proceed to the next chapter of hypothesis testing for two samples. All right. Can you see it? We're going to learn hypothesis testing for two samples. All right. And you can see that let's have a look at the following example. Suppose that you select several subjects and they were asked to parallel park two cars having very different wheelbases and turning radius, and you record the time in seconds that each person need to park each car. All right. So in this case, you have there are two samples here, right? The first sample for the first car and the second sample for the second car. All right. And you see that the numbers here, each you have several pairs, and the two numbers in each pair are correlated, right? If one person is an experienced driver, then that person will need less time to park a car. Otherwise, the person will need more time to park the car. Okay, I mean both cars, right? So if the time one person needs to park the first car is high, then it is likely that the time that the person needs to park the second car is also high, right? Or vice versa. All right, there is no guarantee that it must be high, but it is likely that it will be high. Okay, so we have several pairs, right? We have several pairs here, and each pair give you the time that each person needs to park each car, right? To park the two cars. Am I right? Okay. So in this case, we say that the two samples are dependent. Okay, and you can call them the mesh pair design. Okay. Understand? So the two samples are dependent. However, if I instead of 14 volunteers, I get 28 volunteers. Okay. What if I get 28 volunteers like this one? What if I get 28 volunteers? So you get 28 people, and each person will park one car, not two cars, in random order. In this case, each person only park a car, right? And there are 28 observations here. So you see that there is no relation between these two numbers, right? And you have two samples again, but these two samples are independent. Do you understand? That's all clear, everybody? That's all right? The two samples are independent. Is it okay? Okay. Let's consider another example. Suppose the course coordinator wants to compare the average midterm and final scores, and you can get and then you can get 9 students. Okay, and for each student you can get their you can get his or her midterm scores and final score. Okay, so for 9 students you get you get 9 midterm scores and 9 final scores. Okay, and you see that if a person get a very high score in the midterm, then it is likely that the person will also get a high score in the final exam. All right, so you see that these numbers are correlated. Okay, there might be some relation between them. Am I right? Okay, so you have several pairs here. Okay, and so you come up with dependent samples. Okay, dependent samples. All right. However, if you select randomly 18 students like this one, so you get 18 students, and for each student you get the his or her midterm score. Okay, for the first student you get the midterm score. For the second student you get the midterm score, and so on. But for the 10th students you get the final score, and 11th students you get the final score, and so on. So after all, you still get 18 observations. But unlike the previous case, in this case, you don't there is no relation between these two numbers. No. Okay. So the two samples the two samples are independent. In this case, we see that they are independent. Do you understand? That's all clear, everybody? It is okay? Hello, is that all clear? May I move on? Okay, so you may say that why don't we we just use one of them? Why don't we need to consider the two cases? Why don't we just consider only one case? Well, in general, you cannot always do that. You cannot just make it dependent. Like suppose that you still have the two samples, but you don't get the midterm scores and final score. You get something different, something like this. Okay, let's have a look at this. Suppose that the cost coordinator wants to determine if two ways of taking the cost resulted in a significant difference in achievements as measured by the final exam for the course. So in this case, you get two samples, right? But instead of midterm scores and final score, you get the two groups corresponding to online class on the online class and the conventional class. All right, and you see that you cannot ask a student to take the exam online and in class at the same time, right? It is impossible. That's why there's no ways to get this kind of of design, right? And you have, and then you need to get something like this. You need to get something like this. You see that in this case, you need to get 18 students instead of only 9 students, and each person will take the exam online, either online or in class, right? So you must have 2 independent samples. Okay, you may say, okay, why don't we only use independent samples? Well, it is not a good idea to always use the independent samples. Why? Because if you use independent samples, then there is a chance that you select very good student in for the first group. Okay, very good student, good profile students for the first group, and worse profile for the second group. Okay, so so when you compare the scores, you may see that the average score of the second group is greater than that of the first group. But it may not be the the type of taking the course or taking the exam may not be the main factor. Maybe the students, the ability of the students is the main factor, and you cannot take care of that. Understand? So the dependent samples are good, design is good to get rid of the confining variable, but you cannot always use you cannot always use that. All right, that's why you need to go over. You need to learn both cases. Do you understand what I'm saying? Is that all clear, everybody? It is okay, everyone. It is all right. Hello. May I move on? May I move on, everybody?
Yes, teacher.
Okay, thank you very much. Okay, now I want to give you the outline of what we are going to learn in this chapter. Excuse me. Okay, so in this chapter, there are 2 samples, right? In the first group, there are N1 observations. In the second group, there are N2 observations. Okay, the observation in each group are independent. So X1, X2, Xn1, they are independent. Y1, Y2, Yn1 and 2, they are independent. But the Xi, but how about these two? These two groups, you don't know. Okay. Okay. There are 2 cases. In fact, in the first case, they are not independent. They are dependent. Okay. If they are dependent, then you see that the number of observations in the 2 groups are the same, right? So N1 and N2 are the same, and let's say that it is the N. All right, and we can consider di as the difference between xi and yi. Okay, so we can now we can assume that di follows a normal distribution. All right, and sigma is a no or no. All right, we're not going to consider the case sigma d is no, because in practice you don't really know that. Okay. The second case is that you don't know the distribution of di, or let's say it is not really normal. Then you need the assumption that the sample size is large, so the common value n is large, and we can we can apply the central limit theorem to perform the test. So in this case, you need to use the t-test, right? And again, in this case, you can use the z-test, all right? For the independent samples, it means that the xi and the yj, they are independent. Then we consider the following cases. In the first case, they follow normal distributions. Okay, the xi and the x and the y, they follow normal distributions with different, maybe different means and different variance values. And then for this particular case, you can consider three subcases. Sigma 1 and sigma 2 are known. Okay, the population standard deviations are unknown. And if you don't know them, then we can we do have two more cases when they are the same or different. Okay, if you don't know the distributions of the xi, the x, and the y, then you need the assumption. You need an additional assumption that n1 and n2 are big. Okay, if the sample size are large enough, then we can use the central limit theorem to perform the test. Even for arbitrary distributions or for Bernoulli distributions. For Bernoulli distributions, you can come up with the proportions. Okay, so this is basically the outline of what we are going to learn in this chapter. All right. Okay, now I will continue with the first case when the two samples. When the two samples are dependent. Okay. All right. Let's have a look at the following example. Okay. What do you think? So for the first, by the way, for this case, we assume that it follows a normal distribution, right? So when the sample size is large, is small for the pair samples, we assume that they follow a normal distribution. Okay, because you cannot use any software in doing the same. That's why we just take it for granted. All right. For this one, let's see. All right, so now in this example, there are 14 subjects, right? Only 14 subjects. It means that you have two dependent samples, and you record the time in seconds that each person park each car, park the cars. All right, and then you want to find a 95% confidence interval for the difference in means. How can we do it? Well, all you have to do is to compute the difference between the two columns, right? This is the x and this is the y. So x minus y give you the difference, 19 minus 2. Okay, 25.8 minus 20.2 give you 5.6. 16.2 minus 16.8 give you minus 0.6, and so on. Do you understand? Okay. And you want to get a confidence interval for the difference in means. All you have to do is to look at the last column. Okay, that's all. That's everything you have to do. You only need to look at this column, and then you can ignore the others columns. All right, you don't need that anymore, right? And then you have only one sample, right, with 14 observations, and we assume that the observations follow normal distribution. Then we can use the t distribution to get a confidence interval. That's correct. Okay. So you see that the mu d is simply d bar plus or minus the t value, okay, times the standard error. This okay? Okay. And what is the standard error? Do you remember? For one sample, what you get is mu equals x bar plus or minus the t alpha over 2 times the s over the square root of n. Or you can say this is the x bar plus or minus the t alpha over 2 times the square root of sigma square. I'm sorry, s square over n. Okay, and this is simply and this is called the standard error. And the standard error in this case is simply the variance of the x bar. Okay, it is the variance of x bar. So you can think, you can check, you can come up with right. Okay, so what do you get here? It is simply, you can find the average value of this column, and you know that the average value is 1.21, I think. 1.21 plus or minus the t value times the standard error, and the standard error is it is the s over the square root of n. So I get over the square root of 14. The sample standard deviation of the last column is 12.68. You can double check to get that. Okay, and now you need to find the t value here. And you get the t distribution and alpha gamma is 90%, so you get 90%. And yes, using the t distribution with degree of freedom 13, this is 0.05 and this is 0.05. So you can get that point, all right? And that point is 1.771. All right, so you get 1.771, and this gives you a confidence interval for the difference in means. Do you understand? Is it all clear?
Yes, teacher.
Consider the next sample. Can you think about that for a minute and tell me your answer by using very similar argument that we use for a confidence interval? Case there are six observations for each group, right? And you see that the concentrations at the same location in bottom water and in surface water may be correlated, right? Because if the zinc concentration in surface water is high, then it is likely that the concentration in bottom water is also high. Okay, so well, the two samples here are dependent. Okay, and if they are dependent, then you need to have a look at the difference between that, right? to get 0.430 minus 0.415 is 0.015, and so you get the last row. And you want to test the hypothesis that the true average concentration in bottom water is that of the surface water. So you expect that the this is mu1 and this is mu2. So you expect mu1 to be greater than mu2. That is what you expect. So that is H1. Or let's say mu1 minus mu2 is positive. For the null hypothesis, you get mu1 is less than or equals to mu2. Okay. All right. So instead of comparing mu1 and mu2, I may want to consider mu_d is positive, right? Mu_d is the difference between the average value of the difference. Okay. So you get mu_d is less than or equal to 0. Okay. So now we have only one sample, right? The last row, and you can ignore the other rows. Okay, I can ignore the other rows. We don't need them any longer. All right. So it gets again. Then I need to find the value t. And the value t is the average value d minus the right hand side, which is 0, over the standard deviation on the standard error right here. Then you get the average value of the last row is simply 0.0917 minus 0 divided by the standard error. So you get the standard deviation 0.0607 over the square root of n, and in this case is 6. Do you understand? That's all clear. This okay, everybody? And you come up with the value, the t value 3.6998. Is this all right, everybody? Okay, so you come up with that value t. Okay, now we will reject the null hypothesis if d is too big. If d is too big, you will think that H1 is true. So you will reject the null hypothesis if t is too big. So you get that? And this is going to be, this is 3.6998. So you get, the significance level. Alpha is 5%, 0.05, and the t distribution with degree of freedom 5, I think. And this is the acceptance region, and this is going to be the rejection region. And you get the t value, which is 2.015. Do you understand? Okay. And you can see, you can compare t with that number, and you see that this value is greater than the critical point 2.015. Therefore, we can reject the null hypothesis. Okay, which means that we have enough evidence to conclude that the true average concentration in bottom water is that of surface water. Do you understand? Is that all clear? Is this okay, everybody? May I move on? Good. Hello, is this okay? Okay. We move to the next case when we have two independent samples. For the case when the two samples are are dependent and you do not know if the distribution is normal or not, then you need the extra assumption that n is large enough. So it is very similar to what we learned in the chapter of one sample testing. So you can have a look at that at home. Okay. Now let's move to this case when you have two samples and they are independent. Okay. So I would say that case one, you have the x1, x and 1. They follow a normal distribution with the mean m1, sigma 1 squared, and y1, y and 1, y and 2 follows a normal distribution, m2 sigma 2 squared, and we assume that they are independent. Okay. So you come up with, so you get the xi and the yi. You get the xi and the yi, and you want to compare the mean values of the two groups. Okay, you want to compare the mean value of the two groups. Let's consider one example, and we will learn things through that example. All right. Now let's have a look at the following example. A consumer research organization brutally selects several car models each year and evaluates their fuel efficiency. In this year's study of two similar subcompact models from two different automakers, the average gas mileage for 12 cars of brand A was 27.2 miles per gallon, and 9 brand B cars that was tested averaged 32.1 mile per gallon. And at 1%, should it conclude that brand B cars have higher average gas mileage than brand A cars do? And suppose that two populations have normal distributions with standard deviations 3.8 and 4.3 respectively. So in this case, you know that the average value of x is 27.2. You know that the average value of y is 32.1. You know that the sample size of the first group is 12. The sample size of the second group is 9. You also know that sigma 1 is 3.8 and sigma 2 is 4.3. Do you understand? Okay. And you want to test the hypothesis that the brand B cars have higher average gas mileage. So you expect mu A to be less than mu B. Okay, that is H1. Or let's say mu A minus mu B is less than 0. And the null hypothesis is that mu A is greater than or equals to mu B. Or let's say mu A minus mu B is greater than or equal to 0. Do you understand? That's okay? That's all clear. So this is what we can get, and then this is what we want to do. So we can see that we want to find the z value, right? It is very natural to see that z value is the average value, then minus the right hand side, the 0. In this case, is 0 over the standard error. Now you need to know the standard error. What is the standard error? Actually, the standard error is simply the square root of the variance of the bar, right? Okay. And well, it should be so we need to find the balance, right? We need to find the balance. What is the variance of d bar? So the variance of d bar is simply the variance, because you know that d is x minus y, right? So it is simply the variance of x bar minus y bar. And because x and y are independent, the two samples here are independent, then the variance of the difference is the variance of x bar plus the variance of y bar. And the variance of x bar, we knew that, right? It is sigma 1 squared over n1. And the variance of the second one is sigma 2 squared over n2. Do you understand? And because of that, you can get the standard error, right? You can get the standard error, which is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Is there any questions so far? That's clear. Okay. Then this is what you can get, right? You get the standard error. So back to our problem. You can see that I'm going to make it to have a copy right here. Then the standard error is the square root of sigma 1 squared, 3.8 squared over n1, 12, plus 4.3 squared over 9. And the standard error you can get in this case is 1.8049. 1.8049. All right. And then you can find the z value. The z value is simply the h bar minus y bar minus the right hand side 0. You know, if the right hand side is not 0, then you can change. You need to update the information here. If it is 10, then it should be 10 here, right? Now you have 0, then the standard error is 1. The standard error here, so you get 1.848049 minus 0. X bar is 12. No, wait a second. 27.2. 27.2 minus 32.1. All right, and then you can find the value of z, and the value of z is minus 2.715. Minus 2.715. And you get the value of z, and as long as you get the value of z, you can check to see if it is big or small. If it is, you will reject the null hypothesis if z is too small, right? Too small. Over here, and you get the significance level is 1%. So I would say 0.01 for that. This is the acceptance region, and this is going to be the rejection region. And then you get you can use the standard number distribution to determine the critical point in this case, which is minus 2.33. The value z belongs to the rejection region, so we can reject. You can reject the null hypothesis. Is that all clear? Is that okay, everybody? Is this all right? So we have enough evidence to conclude that brand vehicles have higher average car mileage. It is okay. It is all right, everybody? May I move on? Okay. Let's consider the next sample. That is the sample you can do for when you want to test the hypothesis for two samples, right? This is another example, a quite similar example. Can you think about that for a minute and tell me your answer? Please tell me what you can do with it. And then tell me if you should use which formulation, the first formulation or the second formulation. All right. Okay. Let's consider this example. So you see that you want to test the hypothesis that let's say H1 is that the mu1, you expect that adding in a new ingredient will reduce the drying time. So mu1 will be less than mu2, right? Wait a minute. You expect that mu1 is greater than mu2, right? Adding the ingredients will reduce the drying time. S0 is that mu1 is less than or equals to mu2, okay? Or let's say mu1 minus mu2 is positive, right? Okay. Then you need to find the standard error, which is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And then you get what is that, 8 minutes. So you come up with 8 squared over 10 plus 8 squared over 10. All right, there are 10 specimens in each group. So you get this one, and the standard error is let me see, what do you get with the standard error? So take the square root of 8 squared over 10 plus 8 squared over 10. So you get 3.5777. 3.5777. Okay? And then you can find the z value, which is x bar minus y bar, and then minus 0 over the standard error. And then you get 121 minus 112 minus 0 divided by 3.5777. Okay? And then the value z was that. The value z is 2.5156. Okay? Okay, so you get you can draw the graph here, and you will reject the null hypothesis if z is too big, right? Over here, that is too big, and then you get what is that, 5%, 0.05, and then you come up with the standard normal distribution, and this point is 1.64, right? And the z value is 2.5, which is greater than that. It belongs to the rejection region. Okay, is that a question so far? So we can reject the null hypothesis. That's all clear. for the case when you know the population variance. Okay. Now let's consider the case when you also know the population variance, but you want to get a confidence interval instead of performing a hypothesis testing. Let's have a look at this. Tensor strength tests were performed on 2 different grades of aluminum spars used in manufacturing the wing of a commercial transport aircraft. From past experience, the spar manufacturing process and the testing procedure, the standard deviations of tensor strengths are assumed to be known. The data obtained are as follows. If mu1 and mu2 denote the true mean tensor strengths for the 2 grades of spars, determine a 90% of confidence interval. The 90% confidence interval on the difference in mean strength, mu1 minus mu2. What do you think about it? What do you think about that? Mu1 minus mu2 is simply x bar minus y bar plus or minus z value times the standard error. So it gets x bar, which is 87.6 minus 74.5 plus or minus the z value. Okay. The standard error is the square root of sigma 1 squared. You get 1 squared over 10 plus 1.5 squared over 12. Okay. And the z value you get here, what is that? You have a 95%. The confidence level is 90%. So you get 90%. And then this is going to be 5%, I think, right? And yeah, using the standard number distribution. So this point, I believe, 1.64, right? And you get 1.64 here, and this gives you a confidence interval. Okay, that's all clear. So here's the results we can get. In this solution, you see that I use the number 1.645 because that is the more accurate value. Okay, I use the software, then you can get that. It is same. Don't worry about that. It's fine if you use 1.64 or 1.645. Yeah. Either one is fine. Okay. May I move on to the next case? So far we just learned the case where the 2 samples are independent. Okay, and you know the population variance. You know sigma 1 squared. You know sigma 2 squared. Okay. In the second case, you still have the xi follow number distribution m1 sigma 1 square. Yj follows a number distribution m2 sigma 2 square. And they are still independent. All right, but sigma 1 and sigma 2 are unknown. Okay, you don't doubt that. But we do know something about them. You know that sigma 1 and sigma 2 are the same. Okay, you know that they're the same, but you don't know their values. Okay, what should we do in this case? What should we do in this case? For this case, you need to estimate sigma 1, that's for sure, right? And sigma 2. So you can approximate sigma 1 by S1 S1 is the sample standard deviation for the first group. Sigma 2, you can approximate it by S2. Okay, by S2. And then you can see that we have a problem here. There are two candidates, S1 and S2, but you have only one values to estimate, right? You have a single number, a single value, sigma. So they are sigma, right? They are sigma. So you want to estimate sigma. Should I use S1 or S2 to approximate sigma? You cannot use both, right? You cannot use two values, but you can combine them somehow to approximate sigma to get a more accurate value. So I'm going to use the average value of S1 and S2. And instead of using simply S1 plus S2 over 2, I'm not going to do that. I'm going to use the average value with different weights. So it gets N1 minus 1 S1 squared plus N2 minus 1 S2 squared divided by N1 minus 1 plus N2 minus 1. Okay, and this is and denoted by S squared. Okay, so instead of using 1/2 and 1/2 for the weight, I used the degree of freedom of the two samples for the weight to get the average value of the S1 squared and S2 squared. S squared is called the pool value, and I can use this pool value S squared to approximate sigma squared. So sigma squared can be approximated by S squared. Do you understand? Is that all clear, everybody? Is this all right? Is this okay? Okay. So I get the S squared, and after finding the S squared, I can see that the standard error is simply the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, and then I get the square root. I can approximate this one. Okay, wait a minute. It is simply sigma squared over n1 plus sigma 2 squared sigma squared over n2. So you get the square root of sigma squared times 1 over n1 plus 1 over n2. And you can approximate it by n squared, 1 over n1 plus 1 over n2, the square root of that one. It is okay? It is okay, okay? And now I will denote by SE this value. This is the estimated standard error, okay? Now get back to the statistic. I get T is the average value minus the right hand side, the 0, divided by the standard error, right? And if you use the standard distribution, you need to know the degree of freedom. What is that degree of freedom? The degree of freedom in this case is simply n1 minus 1, n1 minus 1 plus n2 minus 2, or let's say n1 plus n2 minus 2. Okay, that is the degree of freedom. Do you understand? You can also use that to get a confidence interval. Let's say d bar plus or minus the t value times the standard error, right? Is that okay, everybody? It is all right. May I move on? Okay. Following example. Oh, there is one thing I forgot to mention. how do you know if they are the same or different? How do you know that? There's many ways to perform the test. There are many ways to do that, but you cannot use software to read the same. That's why you come up with the following rule, a convenience rule. You compute S1 over S2, the ratio. If it belongs to the interval 1/2 and 2, then we say that they are the same. Okay, we assume that they are the same. Otherwise, we say that they are not the same. Okay, this is not a very accurate method. In fact, it is not. It is the one of the worst methods, but it is convenient. You can do it quickly. And you can use that in the exam. All right, it is okay. Okay, let's have a look at the following example. The cost calculator wants to determine if two ways of taking the course resulted in a significant difference in achievement as measured by the final exam for the course. The following table gives the scores on an examination with 45 possible points for two groups. Do the data present sufficient evidence to indicate that the average grade for students who take the course online is significantly higher than for those who attend a conventional class? Assume that the population are both normal and have the same values, and the significance level is 1%. What do you think? In this case, H1 is that this is mu1, right? This is mu2, and H1 is that mu1 is greater than mu2. That is what you expect. The null hypothesis is that 1 is less than or equal to mu2. Okay, and then you get the t value. T value is x bar minus y bar minus the right hand side 0 divided by the standard error, right? And in order to get the standard error, you need to know the s square, right? And the common value s square is there are 9 observations in each group, so you get 8 times s1 square plus 8 times s2 square divided by 16, I think, right? And then you get the s square, that is 22.2361. All right. And then you can find the standard error, which is the square root of n squared times 1 over n1 plus 1 over n2 equals the square root of 22.2361 times 1 over 9 plus 1 over 9. Okay? Is this all right? And then you get, and then you can get the standard error. The standard error in this case is, let me see. Can you help me with that, everybody? Everyone, you guys, can you get that number? The standard error. It is simply 2.2229, right? Is this all right? Okay. The S square. Oh, the S square. The S square is the let's say you come up with the S1 square, right? And you use this one to approximate sigma 1 square. You use S2 square to approximate sigma 2 square. That is very normal. And you can, but in this case, we see that they are the same. Sigma square, sigma 1 and sigma 2 are the same. If they are the same, then you need only one value. Instead of S1 square and S2 square, you need to come up with a single number, and that single number is S squared. Okay, and you call it the polar value. So you want to use the average value of S1 square and S2 square to approximate S square, correct? And instead of using 1/2 and 1/2 for the weights, I use the degree of freedoms to get a better approximation. So that is n1 minus 1, n2 minus 1 divided by the sum, right? So n1 minus 1 plus n2 minus 1, correct? In this example, there are 9 observations in each group. So n1 is 9, n2 is 9, and then you get s squared is 9 minus 1, 8 s1 squared plus 8 s2 squared over 16. Do you understand? It is okay. Okay, very good. Please feel free to ask questions if you have some. All right. So the standard error in this case is 2.229, and then you can find the t value, right? The t value is the average value. The average value is 35.22 minus y bar is 31.56 minus 0 divided by the standard error. And the standard error is 2.2229. 2.2229. Do you understand? And the t value you obtain is 1.6495. So you get the value of t, and after you get the value of t, the value of t, you can go back to h1 greater than this tail, and this is and alpha is 1%. Alpha is 1%, and yeah, using the t distribution, the degree of freedom is the sum of the two degrees of freedom. So you get 16 for the degree of freedom. Okay, and this is the acceptance region. This is the rejection region, and the value you obtain is 2.583. 2.583, and the number you get t is 1.6495, and it belongs to the acceptance region. So we fail to reject the null hypothesis. Do you understand? It is okay. It is all clear, everybody? Do you understand that? Okay. Now, what if you want to get a confidence interval? What if you want to get a confidence interval? 10 samples of standard cement had an average weight percent calcium of 90 with a sample standard deviation of S1 equals 5, and 15 samples of the lead doped cement had an average weight percent calcium of 87.0 with a sample standard deviation of 4. Assume that the weight percent calcium is normally distributed with the same standard deviation. Find a 95% confidence interval on the difference in means for the two types of cement. Okay, so well then in this case, you need to get a confidence interval for mu1 minus mu2, right? That's all right. Okay. Well, then I get mu1. Oops. I get mu1 minus mu2 equals x bar minus y bar, right? Plus or minus the t value times the standard error. And the x bar is 90 minus the y bar is 87 plus or minus the t value, okay, times the standard error. And the standard error is simply the square root, let's say the standard error is the square root of n squared times 1 over n1, and 1 is how many observations are that? 10 observations, I think. So 10 plus 1 over 15. Okay? So you get s squared times this one. And s squared is the point value. So s squared is let me see, 5, 4. So I would say 9 times s1 squared plus 14 s2 squared over 23, where s1 is 5, s2 is 4, and then you can get the s squared, right? S squared is 19.52. You can also find the standard error, which is 1.796. Okay, so this becomes, I'm going to eliminate this one. We replace what's wrong? The standard error by 1.796, and the t value over here. What is that? The t value, in order to get the t value, you need to use the t distribution. It is a two-sided confidence interval, 95%, 0.025, and the t distribution, the degree of freedom. The degree of freedom is, in this case, is 23. Okay, and then you can get the number 2.069. So you play it into this expression, 2.069. All right, and then you can get a confidence interval for the difference in means. So here is the final solution that you can get. Is this okay? Is this all right, everyone? Is this good? Okay. Is this clear? Okay. Let's have a short break. Then after that, I will move to the case when when the two samples are still independent, one and sigma 2 are different, and you don't know that. Okay, they are still a node, and they are not the same. All right. All right. So let's have a break. Then after that, we will move to this case. Okay.